introduction to Kenta's talk. So we all know about GW170817, and the amount of R process ejected from this particular neutron star merger event is 0.05 solar mass, and this is too high for, according to all the GR simulations, as far as I know. And by itself, if all the neutron star binaries have this much ejecta for R process material, we can easily explain the R process budget of the Milky Way. However, if we believe in the merger scenario and all its implications of it, then we'll run into difficulty in order to explain the abundances, R process abundance of middle porous stars. And this is something that a few researchers have recently pointed out, and Kenta is going to specifically talk about this issue from his set of simulations. So I guess Kenta can start the talk now.
Okay, thank you very much for having me this online seminar. So let me share the screen. Okay. So I'm going to talk about, I'm going to talk about this kilonova in GW170817 and the implication to the R process origin of the Milky Way and the solar system. So the outline of my talk is here. So I'm sorry, I should move this to here. Okay, so outline of my talk is something like this. So I will give brief introduction to this event, what we see after this neutron star merger GW170817, and I will mostly focus on this bolometric light curve, which means the luminosity integrated over all the frequency in the kilonova, and then compare to radioactive power and what we can learn from this bolometric light curve and radioactive power. And for completeness, I will also briefly mention about the photometry, which is light curve as a function of this color, red and blue, UV, near infrared. And also I will show some spectrum and the interpretation. And then I will briefly mention about simulation, what kind of mass outflow can be consistent with the observation. And finally, I will discuss about the galactic R process elements. So here's a brief introduction. So neutron star mergers are very interesting because of gravitational wave source, and also it long has been considered as the origin of R process elements. And also neutron star mergers are possibly the progenitor of short gamma ray burst. And finally, with the gravitational wave, we may be able to get the precision cosmology with the gravitational waves from neutron star mergers. And of course, the last year was breakthrough in this field. We saw this neutron star merger in gravitational waves and other electromagnetic counterparts. And still, one of the big questions is what did we see really in this gravitational wave event in terms of the elements? For example, in terms of R process elements, there are first peak, second peak, also lantanoid elements, and third peak, and what kind of element that we really saw in this GW170817. This is one of the focus in this my talk. And here is the figure from this LIGO-Virgo collaboration, and summarize what kind of, this is timeline of the observations. First, we see gravitational waves, and then we detected gamma ray burst shortly after, like 1.7 seconds after the merger, we see gamma rays. And after 0.5 days after the merger, we start to see this kilonova in UV, optical, and IR. And after 10 days, we started to see some non-thermal emission in X-ray and radio. And actually, these observations now are interpreted as two separated components. For kilonova, what we see is sort of thermal emission from radioactive heating of the R process elements in the ejecta. On the other hand, the gamma rays observed by Fermi and the integral and also the afterglow seen by X-ray and radio is powered by the narrowly collimated jet. So today I will just focus on the kilonova, but I can talk about afterglow observations and theory as well, but it will be another opportunity. So again, this is some summary of what we see in terms of time. So first, after a few seconds after the merger, we see very short pulse of the gamma rays. This is the left panel. We see some pulse in gamma ray duration of about 2 seconds. And this is in X-ray to gamma rays. And luminosity is quite high, like 10 to the 46 erg per second to 10 to the 47 erg per second. And as I said, the right panel shows the light curve of the kilonova and afterglow. So first what we see is quite bright optical UV to near infrared signature. You can see this, for example, optical R band declines from about half a day after the merger, which was very bright, and then continued to decline. And then we saw this signal up to about 20 days after the merger. And then later, on time scale of 100 days, you can see radio and X-ray counterparts, that is afterglow. We call these our afterglow. And interestingly, just counting the energy, total photon energy that we see in each phase is sort of comparable. In each phase, we saw in total like 10 to 47 erg in the photon. So these three phases sort of, we see a comparable amount of energy in the photon. So now I move to the kilonova part, what bolometric luminosity can tell us radioactivity and abundance of this kilonova event. So I should give some introduction about kilonova, and sometimes called as a macronova, so which was originally suggested Lee and Paczynski in 1998, which is this kilonova is the phenomena that neutron star merger ejects some material which unbound, and inside this ejecta there are full of the R process elements, so which radioactively heat up this ejecta. So the right figure shows luminosity versus time. So radioactive power continuously heat up the ejecta, but initially we don't see photons because the expanding ejecta is early time still quite dense, so we don't see the photons escaping from the ejecta. But as the ejecta expands, we start to see some photon escaping from this ejecta. So the photon luminosity goes up to some point, which we call the diffusion time scale. And after this diffusion time, this light curve follows the radioactive power. So basically this time scale is described by opacity and the mass of the ejecta and the expansion velocity of the ejecta. And from this peak, we can also infer what is the mass and opacity and velocity of the ejecta. And as you can see, at later time, the kilonova emission follows radioactive power. So we can, if we get good data for the total luminosity evolution, we can infer what kind of radioactivity is consistently explain the observed emission. So this is what we see. This is the bolometric light curve data. So there are so many observations, so we can nicely calculate what is the total luminosity in the kilonova up from day 0.5 to about 1 week after the merger. So the error bars are quite small in this time, on this time scale. And later, because it's very faint and the signal was seen just in a few bands, so error bars are become large. But still we have more later time, like 20 days after the merger, we have VLT observation near infrared. And also it's very interesting observation by Spitzer telescope at 40 days after the merger and 70 days after the merger. So these data points also tell us what is the lower limit of the bolometric luminosity of the kilonova. And also interesting fact is we didn't really see rise of this light curve. From just 0.5 days after the merger, this light curve continues to decline, continuously decline. So now what I want to do is to compare this light curve with the radioactive heating rate. So let me begin with how to calculate and how to estimate the radioactive power for this kilonova or other astrophysical phenomena. Let me begin with the radioactive power of nickel and cobalt iron decay chain that powers type 1a supernova, for example. This, I think everybody is familiar with this phenomenon. So in the supernova, we know this nickel, cobalt, iron, this decay chain power the energy, and then we can easily calculate what is the radioactive power for this decay chain, which is just two combination of the decay rate of the nickel and cobalt. So we have two kind of bump, one around the lifetime of the nickel and another one is around the lifetime of the cobalt. And just because there are two radioactive elements, we should expect these two contribution. And it nicely fits the bolometric luminosity, late time bolometric luminosity nicely match this observation and theoretical expectation of this heating rate. So we want to consider first how we can get this radioactive heating for the neutron star merger. So for neutron star merger, the situation is very different from this type 1 supernovae, because we have so many different kinds of nuclear radioactive species. So this is famous popular diagram of the proton number versus neutron number just soon after the Arpos nucleosynthesis. And you can see so many heavy elements, and then each radioactive chain decays toward the stability valley with a beta decay. And in this process, the electrons and gamma rays are emitted and then heat up the ejecta. So the situation here is we have so many radioactive species. So one approximation we can take is that we can assume there are so many radioactive elements and statistically adding the contribution of each chain. Yes, so this is how to do it. So left figure shows if you have many radioactive species in a given chain. So what we expect is this d and dt goes like 1 over t. 1 over t is each time some species with the lifetime of about that time contribute to the heat. So d and dt goes like 1 over t. So now the heating rate is d and dt times the energy that released by decay, each decay. So q dot, which is heating rate, is E times n over t. So this is the simple assumption if we have many decay chains and we have many different species of the radioactive elements. And this first paper by Lee and Paczynski just assume, for example, this E is constant with time. So in this assumption, the radioactive heat that you get is just radioactive power goes like 1 over T. But in reality, this energy released by each decay depends on the lifetime of the radioactive nuclei. So we can sort of calculate according to the beta theory of the beta decay, this E of T. So now we know the beta decay, one of the neutron of the nuclei decays to the proton, and in this process we have electron and neutrinos. And then often we expect this beta decay leaves excited state of nucleus, then it decays to the ground state. In this process, this nucleus emits gamma ray, which also can power the kilonova. So in this picture, we can we can calculate energy per decay as a function of lifetime. So this is very simple. So for example, we can just follow the theory that described by Fermi in many years ago. So 1 over tau, which is 1 over lifetime, proportional to the decay probability. And Fermi assumed that decay probability should be proportional to the accessible phase space of phase space volume of electron and neutrino. So maybe this is sort of a golden rule that the probability should be proportional to the density of space, density of state. So the accessible phase space is just the integration of the momentum space of the electron and the neutrino with some energy conservation. And if the energy scale of the beta decay is larger than the electron mass, we can just approximate P as E. So then this case, 1 over tau goes like e to the 5. So this is one thing you can get in this limit. So you can also calculate when electrons are non-relativistic. I'm sorry. Then you can get a little bit slightly different dependence of lifetime on the energy of the decay. So now we can put this dependence on this Q dot. So if the tau goes like e to the minus 5, Q dot evolves as t to the minus 1.2. So we expect a little bit steeper than 1 over t for the decay heating rate. And also we can normalize this Q dot according to just using physical constant involved in this problem. For example, we have fundamental energy scale, which is electron mass, and fundamental time scale, which is defined by this electron mass and also the coupling constant of the beta decay. So then we can normalize heating rate, something like the last line in this. I can't see, but you can. And then this very simple calculation gives you sort of correct orders of magnitude and correct time dependence. So this is how you can calculate the kilonova heating rate by hand. So this is, of course, this is an approximation, but it looks like works well. And you can do this calculation a little bit more carefully, then you can get this heating rate. So Q dot is like 3 times 10 to the 9 erg per second per unit per gram at 1 day, and which goes down, declines with t to the minus 4/3. And actually, this is good approximation as long as you have many radioactive species, and it agrees with the nuclear synthesis calculation of the R process elements. And so this heating rate is actually not exactly the heating rate because this is energy generation rate by the beta decay. But we have to take into account how much energy is actually deposited in the ejecta and radiated in the kilonova emission. So we have to take into account how this thermalization, we call it thermalization process. So initially, the beta decay produces an electron with, let's say, 1 MeV or 0.5 MeV, which loses energy through ionization with the ion. So this process is effective until this time scale shown in the right. so which is depends on the mass of the ejecta and the expansion velocity of the ejecta. After this time scale, the thermalization efficiency becomes less than unity. So we have to take into account this correction. So the actual heating rate is just Q dot shown in upper line times this thermalization efficiency. So now I can compute with just multiply this Q dot and the F thermal, then I can get this kind of line. So this is a comparison between this simple analytic heating rate, which assumes many nuclear species. And this actually nicely explained the bolometric luminosity that we see from 0.5 days to 70 days. And this is, I think, one of the quite strong evidence that we really see many nuclear species, and it's indicative of the R-process element production after this GW170817. And in order to match this normalization, we need like 0.05 solar mass of the R-process elements. Then we can explain the bolometric luminosity. So this is but as you see, you can imagine that this depends actually on what element that we have after the merger, because this calculation takes some limit that we have sufficiently many nuclear decay chain. But you can imagine that it's maybe not the case. For example, if your ejecta is just composed by the first peak elements or second peak elements, then this assumption is not valid. So now we can ask what kind of abundance actually match this observed bolometric data. So now here I show the different composition of the ejecta and observed data. For example, this red line, if you look at the red line is just I take some elements with mass number between 75 and 129, which is just around the second peak. So then in this case, you can see you don't have enough energy to power the kilonova data, kilonova observation around 5 days after the merger. On the other hand, if you take, for example, the elements from 130 to 238, which is uranium, if you take this abundance, actually this can match the data from 0.5 days and up to 70 days. And also it's interesting that, for example, this green line shows just if I take the elements from the first peak elements to the peak of the second peak, then also this kind of heating rate doesn't match the data. So in this sense, we can sort of infer from this bolometric luminosity observation, there are some heavy elements exist after this merger event. And even we can say more about.
Can I ask you a question real quick? So looking at this graph, so I see that the blue and the green kind of overlap, which is blue is 69 to 238.
Yes.
And the green is 69 to 129. And then in between, if you say 129 to 238, this is the yellow. The yellow has power, but I see that the blue matches the green, while I expect that the yellow should be added to the blue in order to get to the green to get the blue.
Yeah.
But I don't see such a behavior. What's going on here?
Yeah, it's a good point. So I should explain a little bit more. So here, what I assume, I take the elements in this mass range using the solar abundance. So if you see, if I say I take 69 to 238. I took the elements. I'm sorry. Yes, all the way from this first peak to the third peak. I mean uranium, and most of the mass, actually, more than 80% of the mass is around the first peak in this case.
Mm.
And if I take 130 to the 130 to 238, which means I take second peak to the uranium, and abundance is
weighted by that. Okay, I see.
yeah. So this is the difference. So anyway, this blue and green both are dominated by the first peak element. So, and interestingly, we can say more about the abundance using this late time Spitzer data, which is about 40 days and 70 days after the merger. These last two data points. So if you look at the lifetime list of the elements, so I just list up the elements with a lifetime of about 10 days to 1 year, which relevant to the Spitzer data at 40 days and 70 days. And you can see there is a gap between iron 59 and strontium 89. So there are no radioactive elements between iron 59 to strontium 89 with lifetime 10 days, between 10 days and 1 year. So which means any first peak element cannot heat up this, cannot provide heat to explain this late time observation. So we can really say that the first peak really doesn't contribute any heat on the Spitzer data. So from that, we can sort of learn that in order to power the Spitzer data at the 43 and 70 days, we need some heavier elements than the first peak elements. So probably the second peak element and the lanthanoids contribute to the Spitzer data. And required mass in this heavy element is also 0.05 solar mass. So this is so Spitzer data sort of requires the heavy elements in this about 0.05 solar mass. Any question so far?
You can continue.
Yeah, sorry. I have a quick question. So the 0.05 solar mass value, that's a fit? Or is it like, I'm trying to figure out, is this something that you get by doing a fitting procedure, or is there some sort of like directly connected observable that suggests that that's the actual mass that we see?
This is the fit. Because basically the normalization of each curve is just proportional to the mass. In order to match the total luminosity, you have to change the mass. And actually, the shape of the light curve really bit depends on the velocity, but it's not so much. So actually, yes, this mass is coming from the normalization of each curve.
Okay.
But of course, the exact value depends on what exactly the abundance pattern. So it's roughly 0.05 solar mass. So now I want to move on to the photometric data and the spectrum. So before explaining about what we see in a neutron star merger, I want to really bit mention about what is special for the lanthanoids. Maybe you have heard about neutron star kilonova is special because of the existence of the lanthanoids, or we expect a red kilonova from lanthanoid-rich component and blue kilonova from less lanthanoid component or something like this. So I show some, I want to give you some impression that why lanthanoids are so special. So here I show the energy level of one of the lanthanoid element. So it's singly ionized neodymium. And as you can see, there are so many lines, so many levels. So this is because you can see these configurations. So there are these 4s, there is some competition between subshells 4F and 4F, 5D, 6P, and 6S. These configurations compete. And there are so many dense lines in the very low energy region that you can see. This transition line about can exist 1 micron, even infrared band. If you compare these levels with some simple atom, for example, oxygen, you can see how simple the oxygen is. So this is singly ionized oxygen that has energy level, just two energy levels in this range. But for the lanthanoid, we have so many levels here. And between this transition between these configurations, we expect some absorption and emission from these transitions. So in fact, you can see here, this is the, in terms of opacity of the neutron star merger ejecta as a function of, for different electron YE, this is electron fraction. So left figure show the mass fraction with different YE distribution. If you look at the orange lines, then which is some broad distribution from YE 0.1 to 0.4. Then you see some heavy elements, including lanthanoids. And the critical value is considered to be YE about 0.25. Then you can see this green abundance pattern, which doesn't really have the lanthanoid fraction, which is about the atomic number of 60 to 70 or somewhere around there. So above YE of 0.25, we don't really expect full lanthanoid rich component. We start to see lanthanoid free component. And the right panel, I show opacity, which is cross section per unit mass, as a function of wavelengths. And once you increase lanthanoid, for example, this orange case, your opacity is quite large. But then YE 0.25, then opacity decreases. And once your material doesn't have lanthanoid, like blue, then your opacity is significantly lower than the lanthanoid-rich case. So this actually impacts quite a lot on the observed signature. And then using this opacity argument, people try to put what is the lanthanoid fraction in the kilonova that we see. So these are several models that suggest some lanthanoid fraction. For example, so different calculation assumes different properties of the ejecta, but they sort of agree that in order to fit the photometric data, the lanthanoid fraction is required to be between 0.1% to 1%. This is sort of agreement that in order to fit this data, this lanthanoid fraction is quite low. And if you take, for example, this abundance pattern, including from the first peak up to the uranium, then lanthanoid fraction is about 0.01. So the lanthanoid mass fraction of 1% means that if it's solar abundance, we have first peak as well as the lanthanoid. So if the minimum mass number of the minimum atomic mass number is around 90, then lanthanoid mass fraction is actually 10% or something like this. But in order to fit this data, what required is the lantern diffraction is quite less than the 10%. And this kind of exercise can be done for also the spectrum. So this is left panel shows like spectrum evolution. You can see just a black data, which is actual observed spectrum. And from 1.5 days, which is very, very similar to the black body. And then after 1 week, we already see some deviation from the black body. You can see some absorption features in the spectrum. And the right panel is more focused on around the near infrared spectrum and compare with the theoretical expectation. So black is data, and the red one is from the some radiative transfer simulation from Duncaisen, and which also infer the lantern diffraction is about 1% of in terms of the mass. So in summary of this Kilonova observation, first from bolometric data, we think there is 0.05 solar mass, but it requires at least second peak, which maybe imply that lantern mass fraction is about 10%. But from photometric data and the spectrum, actually the abundance of the lantern should be lower, like 1%. So it's sort of, I feel it's sort of contradicting, but there may be possible that from photometry and spectrum data, what we see is around the abundance around the photosphere, which is not real, maybe not the representative of the whole ejecta composition. So there are still possible that heavy elements are inside, deep inside in the ejecta, and we don't see them in the spectrum or something like this. Questions so far?
I have a question.
Yes.
This all assumes sort of a solar distribution, right? If mergers would be responsible for this actinide boost, if you had many actinides, would that solve the problem?
Yes, yes. So we don't really. Yes, that's still, we don't really know. But around the photosphere, definitely the heavy elements are not so abundant. But maybe many actinoids exist deep inside ejecta that in a slow component, so that we probably didn't see this huge amount of lanthanoids or actinoids in the spectrum. But yes, if we have much more actinoid and lanthanoid around the photosphere, we are in a problem. Okay.
I have a question.
Yes.
If you reduce the first peak elements by a factor of 10, do you still have a problem with fitting the bolometric data?
We don't have problem if we reduce factor of 10.
Yeah, so in metal poor stars, the first peak abundances typically are significantly less than in the solar pattern.
Right. So yes, so this is also an interesting point that we see in the metal poor stars. We don't see such huge enhancement in the, I mean, first peak elements are not enhanced as much as solar system. That also puzzling in terms of the photometric data and spectrum data, which requires small lantern diffraction, but it's agree with the bolometric data. So let's quickly move on to the mass ejection. So I have a nice animation from David. So now the question is, what kind of mass ejection mechanism can explain for example, first of all, how we can get get 0.05 solar mass in the simulation. Something like this, yeah. Oh no. Yes. So this is a simulation animation provided by David Radice here, I think, in the audience. And this is showing YE distribution and mass ejection. This is now some material ejected at merger. And you can see relatively high YE around the pole, but equatorial plane is sort of dominated by low YE component. So more green and yellow component has high YE and blue has low YE. And as I mentioned, about 2.5 is around the threshold that we have lanthanoid and lanthanoid rich and lanthanoid free components. So here is, oops, for example, some result from numerical simulation, how much we get lanthanoid free component and the lanthanoid rich component. And sort of, it looks like this fraction of the lanthanoid free component from dynamical ejecta looks good for this Kilonova observation. But the problem is the ejecta mass is much lower than 0.05 solar mass. So I can skip this. If you look at this figure, which is a disk outflow mass versus dynamical ejecta that I showed. And dynamical ejecta is always less than 10 to the minus, in this simulation, 10 to the minus 2 solar mass, which is much lower than that we see in GW170817. So now currently we think this kilonova is powered by the outflow from the disk around the formed after the merger. So accretion disk can have mass of like 0.1 solar mass, and some fraction of this disk can be launched through the viscous heating and nuclear recombination heating. So now the current picture is something like this. There are several stages of the mass ejection. First, we have dynamical mass ejection, which that always we see the total mass is less than 0.02 solar mass. And then afterward, this remnant object still ejects some material, and probably which dominates the in terms of the mass of the outflow. So I think now we can say, we can rule out the possibility that dynamical mass ejection dominates the mass outflow of GW170817. So finally, I would like to mention about the galactic RPS element quickly. So now we can say, okay, the total amount of RPS elements produced in this event is about 0.05 solar mass, and the rate estimated by this single event is about 1,500 mergers per gigaparsec cubic per year. And lanthanoid mass fraction may be 10% to 1%, depends on this, if you believe bolometric luminosity or spectroscopy. So now we can compare, we can ask this mass ejection and the rate can be consistent with the galactic R process abundance. And actually it's quite consistent. Here I'm showing the rate in the Milky Way in units of per million year as a function of the R process mass produced in each event. And estimation from GW170817 is around here, this purple magenta square, which I take just a factor of 2 uncertainties factor of 2 uncertainty in mass ejection. And this green diagonal region is the rate and mass in order to explain the total mass of the RPS elements in the galaxy. And also you can see here very strong constraint from dwarfs, which is this nice observations of the ultra-faint dwarf galaxies. This reticulum 2 has our process rich stars, but there are several ultra-faint dwarfs don't have our process rich stars. So we can estimate what rate and mass ejection can be consistently explain the distribution of the dwarf galaxies. So this constraint is these purple circles. So these observations roughly match the data, so roughly match each other. So we think in terms of the total, the rate and the mass ejection, neutron star merger can explain the RPOS elements in the galaxy and dwarfs. However, there is some problem. So in the last 5 minutes, I want to discuss this problem. So in order to understand even though rate and overall rate and mass ejection are consistent with the neutron star merger rate, but now the question is actually the production history of the R process elements is consistent with the neutron star merger scenario, because we expect, for example, oxygen and magnesium, such kind of alpha elements are produced by core collapse, which immediately follows the star formation. But neutron star merger and type 1a supernova delays from star formation. So there are some delays between the formation of oxygen and magnesium and iron and R process elements. So this is some naive expectation from the neutron star merger and type 1a. And also it's true that if you look at type 1a event rate and also short GRB event rate, the delay time distribution actually goes like 1/t. So it's actually shows some delay from the star formation and neutron star merger and type 1a. So now I want to ask if this delay can be really consistent with that we see the abundance distribution of the R process of those galactic stars. So for example, this is alpha over Fe, this magnesium divided by Fe as a function of Fe over H. Then this actually, alpha elements are just produced by core collapse supernovae, and the iron is produced by core collapse supernovae and type 1a supernovae. So roughly speaking, this distribution shows core collapse supernova rate divided by the sum of the core collapse and type 1a. And this data are the observed abundance distribution, and curves are some simple calculation. So this calculation is very simple, so you don't have to trust the calculation around below Fe over H of minus unity. So this gray region, you don't trust this calculation, but beyond Fe over H of minus unity, probably this one zone approximation may work because the time scale is quite long. So then you can see some decline in magnesium over iron as a function of iron over H. So because this is iron increases due to the type 1a, but alpha element doesn't really increase due to the type 1a. So we expect this slope declining magnesium over Fe, which is actually consistent with this observation and theoretical expectation. Now, then here is the R process, one of the R process elements, which is europium over Fe and iron and hydrogen. So because of the delay, actually R process elements and type 1a both delay. So we cannot really make this decline from iron over H minus unity to the high metallicity. We always expect some sort of flat evolution in terms of europium over Fe as a function of metallicity. This is because both neutron star merger and type 1a some delay. So there are some late time contribution for both R process elements and iron, so that we don't really expect this steep decline that we see actually in the stars. So this is actually a bit problematic. We don't see any evidence from this galactic stellar distribution that our process actually delayed from the star formation. But it looks like this decline is quite similar in alpha element and our process elements, which sort of indicate that our process element production follows immediately the star formation. But I don't have obvious answer for that, but some recent papers suggest like, okay, long GRB may have similar situation that we have huge accretion rate disk and disk wing, which can produce also the our process element, and which actually follows the star formation so that this doesn't have this problem. So, okay, let me finish here. Thank you very much. So, any questions?
Okay. You can either write your question in the chat panel or just turn on your mic and speak. Now I have a simple question. So what are the drawbacks of the collapsar model?
Sorry.
What are the drawbacks of the collapsar model?
The difficulties?
Yeah, like why, I mean, is it realistic to assume that kind of the mass of the disk that is assumed in the collapsar model, maybe compared to what you get from simulations of, I mean, it sounds like in the scaled up version of what we see in neutron star mergers, the disk assumption and all, but there is no direct simulation as far as I know to show that the disk mass that is assumed is actually like being shown in simulations. You can get that size of a disk, and there is a debate going on with regard to that, but I don't know.
Right. What I'm not really sure is that for example, the initial condition. So, for example, merger, you can put some accretion disk and then simulate this isolated accretion disk system. But for the collapsar, you have continuous accretion. What I'm not sure is this recent paper done very ideal initial condition that takes some condition that's very similar to neutron star merger, but different Y distribution, and then show the RPOS production. I'm still not sure this is really some realistic situation in the collapsar, but I think so far the collapsar scenario is also interesting scenario that produce RPOS elements. And also in terms of the rate, collapsar scenario is a bit lower, and RPOS production per event is much higher. So I think it's possible that some observation can tell us which is more likely from this rate and mass stuff.
So, do they get the trend of E over FE versus FE over H correct with the collapsar model? I forgot. If they have a plot, as far as I remember, but
They actually, in order to produce this trend, what you need is just no delay or a constant delay. Like constant delay time 100 million years can also explain this. But if you have some power law delay time distribution, like 1 over t delay, then you have some problem.
you have some problem. Interesting.
And another possibility is, of course, this trend is not actually really the representative of the entire galaxy, because this sample of a star is just stars in the solar neighborhood. It's may possible that this trend is just a sort of observational bias. And
oh, I see. Any other questions from the audience? I don't want to take all the time. No?
Kenta, can I ask a question?
yeah, sure.
So just to clarify, you're suggesting that the bolometric light curve implies that the entire red kilonova is coming from just only second peak and beyond?
Right. Okay. What I'm saying is, in order to power the late time bolometric luminosity, what you need is 0.05 solar mass beyond second peak. I mean, including second peak. I'm not saying there is no first peak, but what you really need is the 0.05 solar mass in second peak to the third peak. I mean, yeah, beyond second peak.
And I guess, so my impression was that the total inferred mass was about that mass, though.
Yeah.
I might be misunderstanding, though.
Yes, so I haven't really have quite consistent picture that explain everything. I have to more carefully think that what kind of composition can explain both bolometric luminosity, bolometric light curve, and color evolution and spectrum. So far, on one hand, photometry observation and spectrum requires low mass of heavy elements. But bolometric luminosity seems indicate that there are many heavy elements. So, and both requires like 0.05 solar mass. So this kind of, it's still, there's no clear, consistent picture, but I think we should pursue this complete picture, both the spectrum and light curve.
Okay, thank you.
Well, if there's no more further questions, I guess we all thank Kenta again and see you in a month.